Okay, I'm back, and now let's review what we've learned so far. That there is potential energy, which is energy of position, MGH, and then there was kinetic energy, which is going to be energy of motion. And now what we want to do is connect the concept of energy with the concept of force. So if you recall, force is a push or a pull, and that is given by the letter F. So imagine that you've got this refrigerator here. You're going to apply a force to the refrigerator, and you're going to move it a certain distance r. Well, it's going to take energy to be able to do that. And so the amount of energy it's going to take to move that refrigerator is going to be given by that equation. So the force F that you apply, and then you're going to multiply that by the distance that the object is going to travel, is going to be equal to the amount of energy it's going to take. So this is a fundamental relationship that connects energy with force. Now, this thing that's right here, though, so when you multiply force times distance, that is going to be what work is. So work is going to be given by a lowercase w, and it is going to be the energy that is being transferred from you to the refrigerator. So it's the transfer of energy. And then if you take a chemistry course, you'd find out that there's another way that energy can be transferred from one system to another, and that's going to be through heat. So heat will be the transfer of energy from one substance to another, but work is going to be the transfer of energy through the motion of something. Now look at the units. Notice that since work is equal to the change in energy, we know that energy is a joule, so therefore the units for work are also going to be a joule. Now you might be saying, oh no, that's wrong, because you know that the unit for force is the Newton, and you know that the unit for distance is the meter, so therefore the unit for work ought to be the Newton meter. That's okay. So a Newton meter is also going to be equal to a joule. Not only that, but let's go up here. So this is a unit of energy. So you've got kilograms, and then multiplied by meters per second squared, and then multiplied by meters. And then if you put that together, you would get kilograms meters squared per second squared. That is also a joule. It's just a different way of writing the units. And then if you look at this one, well, this one is going to be the kilogram, and then the unit for speed is the meter per second, but remember you've got to square it, and so you would end up with kilograms meters squared per second squared, which is precisely what you had up here. So there's multiple ways of writing the metric unit for energy, but probably the best one is just to say J for joule. So this quantity is going to be called work. And so here's a sample question. It takes 440 newtons of force to move a refrigerator 3 meters. How much energy did it take to do it? So we're going to write down the force F, the distance r, and then we're looking for work. Then we take those numbers, we plug it into the formula, and we solve it. And then don't forget to put the J on the end, because that's the official metric unit for energy. And then I wanted to compare work with impulse. So if you recall in our previous in a previous lesson, we talked about momentum, and we said that when you multiply the force acting on a system times the amount of time it takes it to do it in, that causes the momentum of the system to change. And we called F times T impulse. Well, so an impulse changes the momentum of a system. Work is F times R, and it changes the energy of the system. So both of them involve force. It's just what do they do. So when you multiply force times time, that changes the momentum of the system, and then when you multiply it by R, then that changes the energy of the system. So let's take a break. When we come back, we're going to talk about examples of conservation of energy.